Okay, so now we're in the topic of constraining forces. Basically, this is a topic where I just want to go over the normal contact force, the frictional force, and the tension force, right? Because these are forces that show up a lot and they are intuitive and simple, but there are some nuances I would like to emphasize. And yeah, so without further ado, let's jump right into it. So generally speaking, these are forces that they prevent some form of motion, right? So perhaps normal contact force, the normal contact force prevents two objects from sinking into each other, right? Assuming that they are rigid objects, they prevent two objects from intersecting. Then the frictional force prevents two objects from sliding, right, with respect to one another. Of course, there's a limit to it, right? There's only so much friction can prevent before the two objects start slipping. And lastly, the tension prevents two objects from going too far apart from one another, right? If you connect them with a string and assuming the string doesn't break, right? And assuming the string doesn't is inextensible also, meaning that it doesn't stretch, right? So if it doesn't stretch and it doesn't break, then tension will limit the distance between the two objects, limit to the length of the string. Yeah, so let's go a bit further into each of these forces. So the normal contact force, there's one thing that I want to emphasize over here, which is that the normal contact force's magnitude, right, can only range from 0 to infinity. The magnitude, if we have two objects in contact, let's say they are in contact like this, right? So suppose the first object is called A and the second object is called B, right? The normal contact force of A on B, right, we'll take it to be this direction as positive. So this direction, right, is perpendicular to the surface, perpendicular to A at the point of contact, right? And this is taken to be this direction is taken to be the positive direction, right? The positive direction for this vector. So the normal contact force, right, it can be greater than or equal to 0, right? However, the moment you try to let the normal contact force of A on B be negative, right, the two objects will just separate. This means that the moment that this vector over here in black, right, the moment it tries to flip direction, when it tries to flip direction, right, that will imply that A is trying to pull onto B, right? It's trying to hold onto B, is attached to B in some sense. But that's not what normal contact force is capable of doing, right? Normal contact force is capable of keeping two objects separate, right? But it does not prevent two objects from normal contact force is capable of preventing two objects from intersecting, right? From sinking into each other, but is incapable of preventing two objects from leaving each other, right? When your two objects are touching, that's 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 the that's the most they can be squished together, but there's nothing preventing you from separating the two objects, right? If not, your butt will be stuck to the chair. So that's something that I want to emphasize. And this question, this important fact will come in useful when there's one question which is quite famous, which is that you have a particle, a point particle on a you have a point particle on a hemisphere, and the point particle is sliding down, right, according to gravity, and you're supposed to find the angle, right, or the height at which the point particle actually leaves contact with loses contact with the hemisphere. And this question, right, even though we're not ready to tackle it now because it requires concepts of centripetal acceleration, this question would emphasize this concept that normal contact force cannot have negative magnitude. Normal contact force does not hold two items together. It always pushes them apart. Okay, so that's something I want to emphasize about normal contact force. The next thing is friction. Okay, so friction is another, just like how the normal contact force cannot pull two objects together, cannot hold two objects together, right? It can only push them apart. The friction has certain limits as well. And okay, so the direction of friction is always parallel to the surface of contact. So if I have a object, let's say a table and a cube on it, right? And let's say there's friction in between. So the cube is, let's call it B, and the table we call it A. So um so assume I take rightward to be positive, right? Assume I take rightward to be positive. So rightward positive, whereas we call the x-axis. There's in this case, friction, F friction, A on B, right? So this is the force on B caused by A, caused by the friction between A and B. Okay, so the force A on B is bounded between two bounds. On one hand, there's mu n, and the other hand, there's mu n. So what does this mean? This means that suppose that the object is just sitting on the surface, right? I'm gonna ask you a question. If the object is just sitting on the surface, right, and the only force right now is gravity, what's the frictional force? The answer is that the frictional force is 0, right? You may be tempted to say that the frictional force is mu n, but no, the frictional force is only bounded by these two bounds, right? Frictional force will always be set to a value that prevents motion. If your frictional force on this object was mu n, like this, then if we consider horizontal forces on the object, right, we see that there's net rightward force, and that causes the object to move. But that's clearly against our intuition, right? When you put an object on a table, and there's friction between the object and the table, the object doesn't just suddenly move out of nowhere, right? So when the object is just resting on the table, the frictional force is 0. Okay, so let me just emphasize that with orange over here, right? F friction equals 0. I cannot draw a vector of 0 length, but I'm just emphasizing with a point over here. Okay, so that's the first scenario. The second scenario is one where the object is sitting on the table, but you are putting your finger over here, right? This is your finger, and you are pushing it with a force F. I'll call it F push. Okay? So question. Suppose there's two scenarios. One is F push is less than mu n, or less than equals to mu n. The magnitude of F push is less than equals to mu n. And the second scenario is that the magnitude of F push as a vector. Remember, F push is the force is a vector. The second scenario is greater than mu n. Okay, so in these two scenarios, question, what would the frictional force be? What would the frictional force of the table, right, on the object be? So in the first scenario, if we take rightward as positive, right, in the first scenario, the frictional force of A on B would be negative of F push. Negative of F push as a vector. So, and the reason is because in order to balance out this force, pushing it to the right, if the object is in equilibrium, then if the object is in static equilibrium, then the frictional force must be to the left, right, and must be equal in magnitude. So the vectors, shall just draw them in equal length. And the reason we know friction would be precisely the magnitude of this orange vector, right? The magnitude of friction is precisely equals to the magnitude of the red vector, the pushing force, right? The reason the two magnitudes are equal is because friction, right, is a constraining force, and you do whatever it can. Remember, you do whatever, you adjust its magnitude, right? Adjust it according to external circumstances to always prevent motion. Okay, so frictional force, in this case, frictional force, right? The magnitude of the frictional force is equals to the magnitude of the pushing force. It is not, right? The magnitude of frictional force is not equals to mu n, right? Unless F push is also mu n. But in general, right, if F push is less than, strictly less than mu n, right? Let's say is a very small amount, then the frictional force would be also very small. So whatever the pushing force is applied, right? In case one where the pushing force is not too much, the frictional force will adjust its value to equal the pushing force. And yeah, so this is a fact that I want to emphasize, because just because the maximum frictional force can be mu n doesn't mean that the frictional force will be mu n, right? If it was mu n, suppose that this instead of the orange vector, right, it was the green vector. Suppose that it was mu n in the opposite direction, so with negative, then that will imply that you're trying to push the object towards the right, right? You're trying to push the object towards the right with the red pushing force. But for some reason, due to friction, your net force, right, is to the left, right? Because the green vector is larger than the red vector. So if your friction was always mu n, then you have a scenario where you're trying to push the object, but then the object is going back against you, right? And that doesn't make sense. So yeah, this is just another example to emphasize that friction always adjusts its magnitude to prevent motion, right? It doesn't always max out its capability. Okay, and in the last scenario, what is the magnitude of friction, right? If your pushing force is greater than mu n, then friction A on B would be minus mu n, right, in the x hat direction, right? If assuming the x hat, assuming x is rightward positive. So friction being a vector, right? Friction being a force is a vector, and the vector has this magnitude, and the direction is negative x hat, right? So that means it's going to the left, which is what the green vector is showing. So in that case, in the second scenario, we have a scenario where the red vector is huge, right? The pushing force is huge, right? And in that case, friction is trying its best. It'll always try to match up to the pushing force, right? Because only when it matches up to the pushing force, it's a net force 0, and the thing isn't sliding relative to one another. It's always trying to match up. So it'll try its very, very best. But the moment, right, it hits this limit, it's like, sorry, the frictional force is like, sorry, I've reached my maximum capability, right? I'm trying my best, but I cannot go for any further. And so it'll just hang in there. Because that's its best. And unfortunately, because the pushing force is greater than the mu n, right? Because the pushing force is greater than mu n, the object will move to the right. It'll accelerate to the right. Okay, so I wanted to emphasize this idea of friction being deep. So whenever I wanted to emphasize this idea that whenever somebody asks you what is the value of friction, right, the first thing you should say is certainly not mu n, right? The first thing you should say is what are the current forces acting on it. Then from there you calculate what's the current net force acting on it, and then you let friction adjust accordingly to make sure that the sliding motion is prevented, right? And yeah, and if only if, right, friction is saturated at this bound, right, is at this inequality, is at the very limit of it, then friction will be stuck there, right? It'll be equals to mu n, and then whatever external forces they win friction, and it will cause the object to accelerate. So that's just something I want to emphasize. There are questions along the way that will require this concept. Specifically, I remember a question where rolling is a great example actually. There's a lot of examples from rolling. If your ball is rolling, what is the friction? What is the value of friction? And there's also questions like your ball is rolling on a slope, right? Those are all questions where that emphasize this idea of friction being adjustable. Okay, so the moment friction is maxed out, the two bodies will start sliding relative to one another. Okay, so something small to take note is that over here, magnitude of friction before they start sliding is mu s. So this is known as static, right? Mu static. The mu is the coefficient of friction, and n is the normal contact force, right? So if your two objects are pushed together very hard, right, then naturally you expect that the friction is increased. Sorry, the maximum friction is increased, right? Maximum possible friction is increased. You see, I almost made that blunder myself. So the mu s is the coefficient of static friction, right? And this is a case where the objects haven't started sliding with respect to one another. The moment your sliding starts to occur, right, you use the friction will be actually equals to mu k. So ironically, when two objects, so usually usually mu k is less than mu s, meaning that when the two objects are already sliding, right, since you use the kinetic friction to calculate the maximum possible friction, your frictional force will actually decrease the moment it starts sliding. So if you're starting to push something, right, maybe you've experienced this when let's say you're moving a house, you push a box on the floor, right? It's quite hard to push. But it feels like the moment you get it to start moving, right, the moment it starts sliding already, then for some reason, right, it's easier to keep going than to suddenly stop. And that's a case where that's a real life intuition for understanding this case where kinetic friction is actually less than static friction. This is true for most of the cases, right? Of course, this is a very empirical approach. The real way you determine coefficients of friction is through experiments. And this is also, unfortunately, a reason why your cars will skid if you lose traction. So let me tell you a story. I was driving on a rainy day, and I accidentally pressed the accelerator too hard. And the moment my wheel started skidding on the floor, right, I suddenly felt like no matter which direction I turned the wheel, right, it didn't follow the direction. In other words, if this is the car, right, if my wheels was pointed to the right, I was still moving upwards, right? For some reason, the direction I steer didn't determine the direction of the car anymore. So this is a case where if your wheel is currently is not sliding with respect to the ground, right? If it's just rolling on the ground, then you have the luxury of having your maximum friction be mu s n, right? But the moment your car tire starts skidding against the floor, right, then your frictional force is only maxed out at mu k n, right? And mu k is less than mu s, right? So that means your maximum frictional force is less. And because you use frictional force to steer the car, right? Because you use frictional force to move the car with respect to the ground, if your car's tires start skidding, then you essentially lose control of the direction of your car, and that is dangerous. So yeah, okay, and so that's for friction. Once again, unfortunately, we're not ready to see those questions where this concept comes in. This concept is emphasized, right? But when we are ready, I'll certainly give you guys those questions. So the last type of force is tension, and yeah, once again, there's this idea where tension, right? Tension. Let's say I have a object A here and B. Tension would keep A and B together, right? But it cannot push them apart. that means that if I consider this direction for A on B, right? So the tension force of A on B, if I consider the opposite direction, if I consider the opposite direction, this direction, to be positive for the tension of A on B, then I have the case where tension of A on B must be strictly positive. Must be greater than or equals to 0, right? It doesn't make sense that TA on B is less than 0. This does not make sense. This is okay. The second scenario does not make sense. And the reason is because a rope, by its nature, is unable to push things apart, right? It's only able to pull things together. So the tension in some sense opposite of the normal contact force. And as for questions that make use of this, there is a question in SJPO special round where you have a pendulum. You have a pendulum like that, and you are trying to find the velocity such that when you throw it, right, it's gonna go up here. But if you have played with pendulum before, you know that if you hit it hard enough, it's gonna go something like that, and it's gonna go up, and eventually, at all these points, right? At all these points is of constant distance, right? All distance L from it. But at some point in time, if it's up here, right, it's gonna start to drop. It's gonna follow like something like this trajectory. And when it follows this trajectory, you can see that the distance, the length of the string is currently shorter than L, and that means that tension is no longer acting on it. So over here, tension is positive. Over here, tension is positive. Here is all positive until the moment over here when it's at this when it's over here, right? When tension equals to 0, then the rope is no longer taut and it starts to drop. So this is a question in SJPO special round that will appear, and we'll go through it soon enough. But we once again, unfortunately for these questions, it just so happens that we need to understand some rotational kinematics before we can tackle these questions. So we'll come to it soon enough. So another fact of tension is that when you have a string, right, whether it's around a pulley, so in some cases you have a string around a pulley like that, so the pulley can rotate, and then your string, you can pull this string in this direction or this direction, right? Or whether it's free hanging, whether the string is free hanging, is as long as the string is massless, right, the tension is always equal everywhere on the string. So this is also called isotropic, and the main reason this happens is if we zoom into a small part of the string, right, and we consider forces. So suppose if at this point, let's say I call this segment A and this segment B, right? So if I consider the shaded part of the string, if the tension at point A, so tension is isotropic, meaning that even though tension is a vector, right, you can think of it as at the end points of the string. At the end points of the string, if it's attached to an object, then the tension would be towards the string, right? If it's attached to an object here, they'll be towards the string. But in the middle over here, this one, when you say the tension here is T at A, right? T being a function. When you say the tension at location A is TA, what you mean by saying that the tension is isotropic means that the direction of this force, right? The direction of this force depends on whether you're on the left side essentially or the right side of this tension, right? So if you're on this side, then the tension will be, if you're on the left side of it, then the tension will be towards. If you're on the left side of it, then the tension will be away, going from the object to the point they're asking. But if you're on the right side over here, then the tension will be in this direction. Okay? So that's just a small tangent on what isotropic means. And tension is not the only force that is isotropic, right? There's also pressure. Pressure is also isotropic. So you talk about pressure in a fluid, right? That's also isotropic. But we'll come to a more rigorous definition yeah, when we talk about hydrostatics or fluid mechanics. So anyway, tension, if you consider forces, if you consider forces on this small shaded segment of string, there's two forces, TA and TB, right? TA is in this direction, right? TA is in this direction and TB is in this direction. So the net force is TA minus TB because they're in opposite direction. So you can see that if there is any net force, right? If there's any net force, if it's not equal to 0, because this string is massless, right? Your acceleration will be infinity. And that, of course, that will adjust the string such that it'll reach a case where the tension everywhere is constant. So yeah, so I'll talk more about the nuances of tension, especially when we go to when we talk about the massive string and when we talk about the Capstan's equation. But yeah, I'll analyze the tension more carefully over there. But just know that this is a short proof for why tension is equal everywhere in a string. And this fact, even though it seems very obvious right now, it is easy to forget this fact. And this fact will be important when you want to solve other questions, right? So tension is equal everywhere in a massless string. In a massless string. But massive string, that's not the case because the string has to kind of hold itself up. So tension will be not a constant function. It'll be a variable of your let's say your height from the ground. Okay, so yeah, so these are just some general. These are the three general forces, right? The three forces, constraining forces: normal, friction, and tension. And now let's go through some questions.